Okay, so this is a new radiation hard scintillator concept for the FCC detectors, for the future FCC accelerators. Basically, there is a motivation for radiation hard scintillator and also wavelength shifting fibers development, and we are working on this in some time. So future and upgrade colliders will really impose many conditions, very challenges. So scintillators, we feel that will play a central role as an active medium of calorimetries. So we are looking for compact, high light yield, high resolution, radiation resistant and fast and cost-effective scintillators. We can see that those for the FCC hadron collider in forward regions about 500 gigarad, which is enormous number. So you can see in this map. So basically, we'll talk about three different type of intrinsic radiation hard scintillators. Recently, we have some commercially available scintillating materials. They are PEN and PET. And PEN is blue scintillation, 425 nanometers. PET is a very common type of polymer, which is used in plastic bottles. And the emission spectrum is about 385 nanometers. So you see this sample set from our lab, and then you can see in the lower figure picture that we can really groove this pen very nicely to put the scintillating fiber or other wavelength shifter fibers in the grooves to transmit to photodetectors. So we mentioned that this basic detector pen related items has 10,500 photons per MeV at 425 nanometers. Regular organic scintillator that we are used to using Saint-Gobain scintillators, they're about the same amount of photons per MeV at same wavelength. And PET's, in fact, less than this, a factor of 5 less, 2,200 photons per MeV at 380 nanometers. So basically, this radiation hard scintillation properties of PEN was studied at 100 megarad, which is 1 mega gray radiation resistance. Here they measured the dielectric and photophysical properties in this investigation, and they found that radiation hard for this effects, and the excitation wavelength was between 270 nanometers and 370 nanometers, and at 650 kilo gray, we lost only 2%. Of the light, and 1023 kilo gray, about 5% or so. So we did laboratory measurements for this in our labs. So basically, PEN peak to 110 is about 62 nanoseconds, peak to 1E about 27 nanoseconds. PET is in fact a bit faster. So peak to 1E is about 6.8 nanoseconds, peak to 110 about 12 nanoseconds. So we took these samples to CERN test beam, 150 GeV muons at CERN. And here that you see a PEN light yielding about up to 30 femtocoulomb. And then this is charge. And PET is really a bit less, about 20 femtocoulomb. PET is faster, but emits less light, and PEN is also radiation hard up to 10 megarad that we studied before, and has significant light yield, but is also a bit slow. So, and also we compared this to other type of scintillating materials that we were studying since a long time. So this is the HE, is that our regular scintillators from the Saint-Gobain, PET, PEN, this is our new studies. PTP is a new material that we coat on our quartz plates, and the anthracene and the HEM high efficiency mirrors. So with this beam measurements, basically we use 2 to 4 millimeter thick PEN and PET tiles to read out with green wavelength shifter fibers to get our photodetectors, which is at using 150 GeV muons. And you can see number of electrons you measure in both pen and PET tiles. And since then, we started getting new type of scintillator development. So they're called Scintillator X. So these scintillators have base material and then primary floor and the secondary floor. The main scintillating comes from the primary floor. Secondary floor wave shifter absorbs the primary emission and re-emits the wavelength that is desirable for optimum efficiencies. So you can see basically primary floor PTP emission spectrum. Primary floor is the PTP material. Secondary floor is that BIS MSB. And you can see absorption emission spectra. They fit very well about 380, 400 nanometers, which is the good PMT quantum efficiency region, and therefore the maximum efficiency to measure this light. So this is our production in our labs. So we produce many finger tiles, but they're by 3 centimeters by 6 centimeters. And then we could also, we can see here is that we can make grooves in the middle where we can put scintillating fibers or wavelength shifter fibers. And you can see in the below here in the left corner, these are electronic controls. We developed the circuitry for this. And then also on the right, you see that we modified oven that we can adjust the temperatures during this cooking process. And you see that after we produce our scintillators, they light very nicely blue. And we also took this in our test beam at, again, CERN. And what we did was that we coupled this with the SiPMs, directly coupled to the dimple we made out of the scintillators, Hamamatsu SiPM. The tie size was 3 by 3, and then here you can see that we adjusted beam with the wire chambers that we can really focalize everything on our scintillators, and you can see beautiful spectrum as a function of charge events per every 6 femtocoulomb, and you can see using the SiPM all the 1 electron, 2nd electron, 3rd electron peaks very nicely. And basically polish side of the dimple that we had to put our SiPM, you can see that basically 18 PE, that light collection. And then unpolished ripple, which gives about 14 PE. So basically this data was fitted to Gaussian and Landau type of the distribution. And also we moved our tiles to FirmLab test beam, and we did direct PMT coupling test using clean quartz. Eventually we put PTP on the quartz, but here, this is the clean quartz results, our pen and Scintillator X tiles. And here we used the FirmLab 120 GeV proton beam, and we used the Hamamatsu 7600 multi-anode PMTs coupled to edge and then scope. So basically, clean quartz shows a single tile with reflected wrapping. So this is 1 millimeter clean quartz tiles. And we have 5 tiles with no wrapping, which is a red plot, shows about 4 number of 4 photoelectrons. And then if you put 5 tiles with individual reflective wrappings, so in fact, this number of photoelectrons increases to almost 6, 7. So in fact, there's a linear relation if you increase number of tiles. So in fact, starting from the 1 millimeter tile up to 18 millimeter tiles. So we can see the linear increase of the light and the number of photoelectrons increasing up to almost 22 photoelectrons. Again, the very similar fit that I showed before. Number of photoelectrons you see about 10 photoelectrons for this with small sample that we have 2, 3, and 6 millimeters, 2 by 3 centimeters plus 6 millimeters. The edge coupled and the PMT is that part is polished. But however, we didn't know reflective wrapping in this basic system. So Full width half maximum 110 is about 15 nanoseconds. So this is extremely fast. So we went to do some radiation tests for these devices, and now we go Scintillator X system. We tested at CERN with the 40 megahertz proton radiation, and we only lose 7% of transmission after 40 megahertz proton radiation. So you can see this basic transmission curve and transmission before and after shown in this basic plot. And similarly, if you go the excitation emission spectrum before and after radiation, and you see that there are very little changes, so almost no change on emission absorption after radiation. So this is a very good signal for this. For the PEN, we studied this at Michigan State University gamma source, cobalt 60, 1.33 MeV gammas. And we had two samples up to 1.7 megarad in air and 10 megarad in nitrogen. And you can see the behavior here, and then we analyze this after getting the samples in our lab. So, and you can see that between 10 and 1.7 megarad air or nitrogen and undamaged portion. So again, damage is not very, very large in this situation. And we carried on doing this radiation damage tests at Iowa Hospital gamma source, which is a cesium-137. And we went up to 1.4 megarad and 14 megarad. So you see the results here. Obviously, after initial irradiation, you see damage, very high doses. And then again, all the scintillators started recovering here. So we can see PET results here. And in fact, we published some of these ideas. And initial damage, permanent damage, and time recovery, these are three important factors studying this. PEN and was damaged more than PEN initially. Permanent damage was same as at 14 megarad, almost they reached the same level. So PEN was recovered in 5 days, so as a recovery, and PET in 25 days. So it was very slow recovery time. So we have another thing that going on, that we do LED stimulated recovery system. So we build electronics and to do this job. So the question was, can we stimulate recovery scintillating damage from the radiation? So basically we had three colors, red, blue, green LEDs in the circuitry. And then we can see that we can put different type of materials, PEN after 3 days and PEN after 7 days. And you can see that recovery is coming very, very nicely. And also we measured the different materials, commercial EJ260, Elgin, and overdubbed version EJ2PP, and also our Scintillator X in this basic LED stimulated recovery principle. And you can see that in this basic Scintillator X, Elgin and Elgin doped. So Scintillator X showed significant effect sample on this LED recovery, 10% more and faster. And neither Elgin materials showed any effect because they are really in green emission. And the blue scintillators respond to color spectrum, but green scintillators are affected very little. So basically, idea is that we can implement this kind of stimulated recovery electronics directly on the scintillators for the real experiments. Conclusions here. The options intrinsically radiation hard scintillators are being expanded with the addition of Scintillator X that we developed recently in our labs. So they're extremely radiation hard. And we can really tune this scintillating material with different variants of the Scintillator X and different doping and different cooking cycles. And we hope to improve this even further and try to make the best radiation hard scintillator ever possible. I didn't talk about the wavelength shifter fibers studies in the stock, but there's also wavelength shifter fibers development also going in our labs regarding radiation hard wavelength shifter fibers. Thank you.